Welcome back to our discussion of spatial query languages. In last few videos, we discussed the notion of queries, the notion of query languages, and then we went into the details of SQL query language. We saw single table queries, multi-table queries, and even nested queries. All this was preparation for us to appreciate the spatial aspects in SQL. So we are going to do one last step to motivate why spatial data types and operators were added to SQL. So in this particular module, we are essentially going to look at that motivation. And in particular, we will visit a notion called the semantic gap. So the old SQL, it was not convenient to express spatial data types and spatial queries. People use two different terms, semantic gap, meaning that it's a lot of work to express spatial queries in old SQL. Some people also use the word impedance mismatch. So if you are an audiophile, you probably remember that if your speakers are not well matched with amplifiers, bad things happen. And that was another analogy people used. Okay. So let's continue on. Okay. And think about what we saw in SQL so far. So we saw some basic data types there, such as numbers, strings, date, and currency, but we did not see any spatial data types. So if we wanted to express spatial data using these simple types, it was inconvenient. So consider this simple spatial data where you have a rectangle with 4 corners, which are named P1 through P4. Okay. Suppose we want to express this data using the old SQL using numbers. Okay. Then it will require fair amount of work to represent the geometric data types such as rectangle. Okay. So let's see some details now. Okay. And we may then have queries on this workload where we may want to list all rectangles which contain a given point as a corner point or the given point as an inside point. Okay. So this is a very, very simple spatial workload. The real workload tend to be more complex. So instead of rectangles, we may have polygons, and instead of inside, you may do many other geometric operations. But these simple examples probably are sufficient to illustrate the inconvenience imposed by old SQL. Okay. So let's first think about how we model this data in old SQL. Okay. So if you wanted to model points, rectangles, and so on, then we'll need many, many tables. And one reason for that is a table design philosophy called normal forms. So in traditional SQL, there was an insistence on reducing redundant data. And the idea was to reduce risks of inconsistent data after update. Multiple copies of data have a risk that one copy may get updated while the other copy is not, and your data quality goes down. So because of that, in traditional SQL, they put some design restrictions. One of, in the third normal form, there are 3 restrictions. So one of the restriction, which is actually first normal form, says that every column in a table should have a simple atomic values. You should not have multi-valued attributes. Okay. Now, if you think about this rectangle has 4 corners, P1 through P4, and this normal form design discourages keeping all that in one table. So your only option is to break it into multiple tables. And one way to do that is to have a separate point table where you could store the 4 corners. Okay. And then in order to connect these points to rectangles, we may even need this edge table. So edge may be this straight line segment. P1, P2 is a side or an edge. P1, P4 is another side and edge, and so on. Again, since the first normal form doesn't allow 4 edges to be associated with a rectangle in a single table, we need to break it out and put it in a separate table where 4 different rows may be placed. Okay. And then finally, to connect these points to edges and edges to rectangle, we need other tables. So to connect points to edges, we may add a table called starts or ends, where you may say, well, if I'm looking at an edge P1, P2, it starts at point P1 and ends at point P2. Okay. And then finally, to connect edges to rectangle, you need a boundary table. Okay. So this simple geometric object rectangle, which all of us may think of as a single unit conceptually, in relational database, it may get broken into 5 tables. In addition, each table may have multiple rows. So the 4 corners go in the point table, and there are 4 rows in the point table. Okay. There is 1 row in rectangle table for this entire unit. Okay. Then for 4 edges, we get 4 rows in the edge table. And then to connect edges to rectangle and edges to points, you have additional table. So here is the boundary table which says the rectangle R1 has 4 different edges, but it's shown as 4 rows rather than a single row with 4 different values. And then to connect edges and point, you again got several entries in starts or ends. Okay. So try to imagine just a simple thing like a rectangle. To represent that in old databases, you have 5 tables and almost a dozen different rows. Okay. If you want to take an analogy with your real life, and this was something that was discussed a lot in 80s and 90s, they said imagine if your house had a relational garage. Okay. Then at the end of the day, when you bring your car back, it will ask you to take the 4 tires out and put it on one shelf, one at a time, and the 4 seats out and put it on another shelf. And in the morning when you're ready to drive the car back, you have to assemble it back, and that was the life. Okay. So it certainly leads to performance issues, but also it leads to inconvenience if you want to query. So let's see what these queries look like. So remember the first query, which was very simple. So let's say I had a set of rectangles, and then given a particular point, I want to know which rectangles contain the point. Okay. So to express this in SQL, you may actually consider writing it yourself before you see the solution in the slide. And this will help you exercise and build on your skills on SQL. Okay. But the basic strategy would be that you join all these 5 tables, okay, because in order to collect your rectangle information back together, you need information from all 5 tables. And the join path is a natural join path, because there are matching attributes across table, so you can use those to join. And once you have done that, then we can test that at least one of the points associated with the rectangle at hand has x coordinate 0, y coordinate 0, because we are looking at origin, which is x0 and y0 point. Okay. So again, quite likely we have done enough SQL that you should be able to write this query on your own, and the basic relational algebra will allow you to express it in a reasonable manner. Okay. But even if you could do that, we should note that joining 5 tables is expensive. It will take a while, your queries will run slow. And in addition, for average programmers, joining 5 tables is not a natural thing. Getting them to join 2 tables is a big step forward. Getting them to join 5 tables means that a lot of programmers won't want to do this. Okay. All right, so this is just the beginning. Now let's look at the second query, where we are looking at rectangles which contain a given point. So maybe you have a city center and you want to know all the rectangles which contain the city center. Okay. Now in this case, the predicate to test inside is even more difficult, because in order to test inside, you may consider the opposite point. So in this case, the left bottom corner and right upper corner, we may need those 2 points. And then if another query point is inside, you could compare and say the query point x coordinate is between the x coordinate of lower left and upper right coordinates. And same thing about y. Okay. So here, this will be harder. And again, just as an exercise, you may want to try it, particularly if you have some experience with SQL, then you certainly ought to try it to realize the pain everybody went through. Okay. So again, I'm not going to worry about whether you can write it or not, but let's at least look at one way to do that, okay, and see how tedious it is. So your basic strategy is to essentially assemble the information back about each rectangle. Okay. Once you have done that, then you can essentially determine the smallest x and the largest x across the points of a rectangle and so on. Okay. So to gather it, the strategy is very similar as before. We basically go through all 5 tables and we do the natural join. Okay. And then in order to compute the lower left corner and the upper right corner, we can use the aggregation query. So suppose this join result is grouped by the rectangle ID. So in other words, all the points of a rectangle get into one group. Okay. So all the x coordinates and y coordinates associated with 4 coordinates of a rectangle, they are part of one group. And in that group, you could compute the minimum x, minimum y, maximum x, maximum y. So using this aggregate query over 5 table join, you would have determined lower left corner and upper right corner. Okay. And once you have done that, then we can essentially put a additional qualifying criteria to test the inside, okay, where we are saying the query point must be in this range, minimum x, minimum y, maximum y, and that may look like this. Okay. So again, you can a very simple query. If you were to write it in Java and so on, you won't have to think as hard. But in the old SQL, the code was tedious, and it required fair amount of skill to do that. And that's why people use the terms like semantic gap or impedance mismatch. A very simple task was very hard to accomplish using old SQL. And again, remember, the workload we gave you is not very hard from spatial perspective, because in spatial data we often use polygons. So try to now imagine if I had a convex polygon, computing inside requires a lot more thinking than this. Okay. So I hope you will agree that it was very painful to write spatial queries in old SQL, and because of that you can realize that many programmers came and complained, and they motivated the SQL vendors to move up and support user-defined data types. Okay. So once you have user-defined data type, this complex query will not look as hard, and in fact you may write it like this in the new SQL. So in this case, you notice very simple, one table, and all the information is contained in this table, and you can essentially use predicates like within. So inside, outside can be directly modeled and provided as a library. So you can look at the polygon shape of a rectangle, you can look at a point and simply ask for this predicate, which will be something you probably would have expected having done some programming in object-oriented languages like Java or Python and so on. Okay. Of course, in order to support this query, the table design will change, and your new table design may have a single rectangle table with ID, name, and the shape polygon. Okay. And you may have a separate point table. So again, you notice the table design and queries get much simplified if we used object-oriented programming. Okay. So this hopefully motivates the need for new spatial data types and operations. In the next video segment, we are going to go and see a common library called OGIS library, which came in mid-90s and since then has been widely adopted. So most commercial or public domain software dealing with spatial data types and databases use this particular library. Okay. So we'll see you soon with the next video, where we'll go and look at the actual spatial data types and operations which are available today.